My talk today is on universal adversarial perturbations and how we can use neural networks to learn to generate these perturbations. And this work was done jointly with my supervisor, George Denizis at UCL. So most of you are familiar with adversarial examples, so I probably... Sorry. Most of you are familiar with adversarial examples and what they actually mean, so I'm going to skip that part of the talk and just go into what transferability means. So transferability in adversarial examples means that the adversarial nature of the image remains adversarial when you put it into a different model that hasn't been used in the crafting. So for example, here we have an adversarial example that's been crafted against model 1 using the FGSM, I think, and then when we go and input it into model 2, the adversarial nature of the example remains the same. So it's actually misclassified by this new model. So why do these adversarial examples actually do transfer? So instead of me explaining, I'm going to use a paper from last year's ICLR that explains it quite nicely, well, or at least attempts to, where they essentially plotted the decision boundaries of a few different ImageNet classifiers for this specific image here along two orthogonal directions, so one being the gradient direction and one an orthogonal one. And the colors here represent the different decision boundaries. So the dark blue class in the center represents the actual true class of this fish. Okay. And you can see that they're all quite similar. But if you take a few steps in any direction away from the gradient direction, you'll see that you'll soon get a misclassification, and this misclassification would be replicated if you then transferred it to any of these other image classifiers. So in the most extreme case, it's possible to construct one single perturbation given an image data set and a model that tried to classify this data set. And you can apply it to any image, and it will most likely fool this model. So this was first discovered by Ian Goodfellow and his co-authors, and it was developed into an actual full analysis by Musavi Desfouli and his co-authors a couple of years ago. And they used deepfall, which is an iterative, and they used deepfall to do an iterative attack and to learn to craft this adversarial perturbation. So formally, we define a UAP to be an adversarial perturbation that is agnostic to the image that is being applied to. So given a target model and a data set, we construct this single perturbation that for any image within a data set, and the probability that the decision between the original image and the adversarial image is different. The probability that it's different is quite high. And we also constrain it to be within some LP norm, some small LP norm. So the question we asked was that can neural networks learn to craft these UAPs? Aside from it being an interesting academic exercise, there are some advantages that neural networks can provide when learning to craft these attacks. One is that after training, inference is pretty much free, right? The cost of actually generating these adversarial perturbations is essentially negligible compared to other techniques that you would have to rerun this attack to create a new adversarial perturbation. So the way that we do this is pretty fairly simple. We just sample from some latent space, and this is then transformed into a perturbation given by this adversarial model, and it's scaled to be constrained within some epsilon ball. And then it's applied to just some random image, we just randomly sample from the data set and combine the two, clip it to some constraint to the target model's acceptable input ranges, and then classify this new example. And we essentially train the adversarial model based on this objective function here, which looks a bit horrible, but essentially all it's saying is that we want to minimize the most likely class and maximize the second most likely class. And this kappa essentially just says how confident we want this target model to be at misclassifying this example. And then we have this additional term that tries to minimize the LP norm of this perturbation. And we scale such that, so we scale such that the difference between the norm of the perturbation and the norm of the data, the inputs to the data set is pretty small. So these are three UAPs for 3 different ImageNet classifiers, so Inception, ResNet, and VGG, that have been created by this adversarial model. And at the bottom is the original ImageNet test set accuracy, and below that is the adversarial example version of that test set. And you can see that the target model is about 60 to 50% worse at classifying these adversarial examples. And these are just some other pretty pictures. So you can see that ResNet misclassifies this table lamp as a cat, and VGG, for example, classifies this radio telescope now as a breed of dog. Other cool things we can do is that we can actually do targeted UAP attacks. So instead of just asking for any misclassification, we can ask the adversarial model to make sure that we generate a UAP that will generate a perturbation that, given any input to the data set, when it's combined with this UAP, it will be flipped to this specific attacker class that we care about. And all we do is, instead of minimizing the LNT objective function, we minimize this one below it that basically says that we want to maximize the attacker chosen class and minimize the other most likely class. And doing that, we can get some other nice images. For example, these are 3 different examples of targeted UAPs for the golf ball class. And so all the images on the left are essentially the correct inputs, and on the right is the adversarial examples. So they're all classified as golf balls with pretty high confidence. And you can actually see, interestingly, in the middle one, for example, the middle UAP, the actual UAP has some kind of structure, some kind of visual representation of what actually a golf ball looks like. It's got these kind of hexagonal patterns. Other cool things we can do is that we can actually completely enumerate the targeted UAPs that are required for CFAR 10, because there's only 10 classes. So these are all targeted UAPs for every single possible class in that data set. So the diagonals represent the actual true images, and the off diagonals are UAPs applied to one of the classes. And they look pretty similar, in my opinion. Okay, so adversarial training has been, among thousands of other defenses, has been proposed to try and improve the robustness of models against adversarial examples. And the main thrust of how it does that is it tries to optimize an objective function that includes some adversarial examples. So if the target model has seen these adversarial examples in the past, hopefully it will do better at classifying them in the future. So we decided to see if this kind of defense would be useful to defend against UAPs created by this adversarial model. So we played this kind of cat and mouse game where we train an adversarial model to create these UAPs, and then report the target model accuracy on the adversarial examples that have been generated. And then in the next step phase, we defend this target model using adversarial training, using the adversarial examples that have been created by this adversarial model, and then report the defended target model accuracy. And then we go back to 1 and create and update this new adversarial model based on the defended model. In this way, so this is the image for that game for CFAR 10. So rounds represent like one step of this game, and this is the target model accuracy for CFAR 10, and we have the green blobs are the accuracy on the defended model, and the red crosses are the accuracy after we've run this new attack. You can see that after about 20 to 30 rounds, there is some kind of equilibrium that's been reached, right? So there is no kind of utility in running this attack or this defense more often, because you kind of know what the accuracy will be on this target model, defended model. Quickly before I wrap up, the adversarial machine learning is a scarily fast-paced field to be in, and so it wasn't a surprise when 3 preprints within the same week appeared doing the identical things. So my paper, a paper by Porseed and his co-authors, and Mupori and his co-authors, they basically all do the exact same thing, and they are both very good papers. So if you're interested in this work, as well as checking out my paper, I would encourage you to check out those 2 other papers. Sorry, thanks.
Is there any questions?
Very nice work, thank you. I noticed the generalization here. The past work generated a single universal perturbation, and you generate a distribution on that.
Yeah, we want to sample from that space.
So I'm wondering if you can say about what why it's useful to be able to sample from the space, and also if there was anything in your loss function that encourages the network to generate multiple ones as opposed to just being a constant function that always outputs the same one.
So we did some very preliminary analysis of the similarity between successive samples from this space, and we found that they're not identical. There is some kind of difference between them. So annoyingly, the paper by Mopori and all did actually do what you exactly suggested, and so they had this kind of extra term within the objective function that penalized similar UAPs that have been sampled from this adversarial model, and so so they managed to generate much more different UAPs from using that kind of idea, which we didn't do, annoyingly.
Thank you. Actually, I also have a question. So, have you tried the very adversarial retrained model? How the attack success rate is for for example, the adversarial retrained model, like the robust model from the Amnesty challenge?
Sorry, can you repeat?
So if some model have already been adversarial retrained, they are already kind of robust, and have you tried how this perturbation will be successful on those models?
No, we haven't tried anything like that. Future work, I guess. Sorry.
Okay, thank you. Yeah. Okay. Yeah. Thank you. Thank you for our speaker.